Hello, everyone. I'm Tanuja Kopal, contributing editor for Lab Manager, and thank you for taking the time to join us for our Product Spotlight webinar hosted by Lab Manager in partnership with Sigma-Aldrich. Michael Wright and Craig Orend have joined us today to discuss why selectivity in chromatography and sample prep in LC-MS analysis is so very important, and the clinical impact it can have on enhanced resolution of vitamin D metabolites. Michael is a senior scientist with 15 years of quantitative HPLC and mass spec experience in the clinical diagnostic sector. He has been involved in the fields of newborn screening, gastrointestinal permeability testing, investigation of metabolic disease, endocrinology, and therapeutic drug monitoring, amongst other clinical chemistry applications and analysis. He is currently the section leader for the Clinical Chemistry and Endocrinology LC-MS division at the Prince of Wales Hospital in Sydney, Australia. So I'm really grateful to Mike for staying up so late to be with us live. Craig Orend is a principal research scientist at the Supalco division of Sigma-Aldrich. He provides applications development for both chromatography separations and sample preparation. Craig's primary role is in the support of bioanalytical method development for small molecules, along with R&D product development for sample preparation with an emphasis in mass spectrometry. So as our speakers today are going over their talks, if any questions come to mind, please type it in. You have a question box that appears on the left-hand side of your screen. So all you have to do is type in your questions, comments, ideas, and just hit submit. I will be receiving those comments right away, and we will go over all your comments and questions during a Q&A time after the two talks are over. Today's webinar will be archived on Lab Manager's website, and we will be sending you the web link via email in a couple of days. You can use that link to go back and review parts of the webinar that you may have missed, or you can even forward it along to colleagues who are interested in this topic. However, please make a note that you will not be able to download any slides from our archive on the website. For a copy of the slides, you will have to reach out to our speakers, and we will be sharing their email addresses with you in our closing slide. Also note that the webinar platform is really very user-friendly. You can move things around on your screen. The slide window can be expanded if you need to better view the text. There's also a resource widget. You can download resources related to this topic that are posted there, and the resource widget can also be moved so that it doesn't overlap with your slide window. So again, feel free to play around with a few things on the screen. But without any delay, let me welcome Mike at this time. Mike, again, thank you for staying up so late to be with us, and welcome.
Thank you very much for the introduction. And it is 1 o'clock in the morning here, so apologies to everybody if I sound a little bit vague at times. Okay, so this is going to be part one of the presentation with Craig presenting the second half. Although this will be a little bit like watching a Quentin Tarantino film, because you'll be seeing some of the end of the story at the beginning, where we show you the application that we developed using the technology before Craig actually explains what the technology does and how it works. So the application that we looked at was improving the measurement of serum 25-hydroxyvitamin D when we look at assessing a patient's vitamin D status in a clinical diagnostic setting. So for those people who are not from a clinical background, or who may be from a clinical background but not involved with clinical chemistry or endocrinology, I'll just give a very brief background to why we measure a patient's vitamin D status. So vitamin D is known to be heavily involved in calcium regulation. That's pretty historical. We've known that for quite a long time. And deficiencies in vitamin D, known to cause rickets in children, have possibly plays a role in osteomalacia, and there's some evidence for and against having sufficient vitamin D protecting you a little bit from osteoporotic fracture. But in recent years, there's been a fairly strong correlation between vitamin D status and your immune system. And then following on from that, we saw an enormous body of work come through the literature where basically vitamin D was linked to pretty much every single disease that we knew. Now, I'm not obviously a I'm not saying that this is all definite fact. A lot of this stuff is still highly contested, but it's suffice to say that the general interest in measuring a patient's vitamin D status has gone up dramatically over the last, we'll say, 10 or so years. Now, when we talk about measuring vitamin D status, we often talk about measuring 25-hydroxyvitamin D. Now, this metabolite is generally what we measure when we're looking at vitamin D status. So vitamin D, you get predominantly most of your vitamin D from the action of sunlight on your skin, but you can also take vitamin D in through your diet. You get vitamin D3 through fish and through meat. In vitamin D2 you can also get, which usually comes from supplements. Although in Australia we don't generally supplement people with vitamin D2, we usually use vitamin D3, and I believe that's the same in the States as well. Whereas in Europe and in Asia you do see a reasonable amount of patients that have been supplementing with vitamin D2. Now all of these vitamin Ds are hydroxylated in an unregulated way in the liver. So as soon as they reach the liver, they receive a hydroxylation at the 25 position, which turns them into the metabolite 25-hydroxyvitamin D. Now that circulates around in the bloodstream until your body requires vitamin D to take effect, whereas signal is sent to your kidney, and your kidney then hydroxylates the vitamin D metabolite again, this time at the 1 position, and makes 1,25-dihydroxyvitamin D. And that's the active form. That's the form that does the work. But it's not a good way of measuring vitamin D status in a patient because it's only present when you actually need it. It's present in quite low levels, low picomole levels, and it doesn't have a particularly long half-life. So generally, because the 25-hydroxyvitamin D metabolite is the most abundant metabolite in circulation, that's the one we usually measure when we're trying to work out if you've got enough vitamin D or not. Okay, so as I mentioned before, there's been quite a large increase in interest in this measuring this metabolite. This is just a graph of the number of requests we got for this in the lab where I was working in Cambridge in the UK. And just in the space of, say, 10 years, the number of samples went from 500 a year to about 10,000. And that continued to grow to 20,000, 30,000 samples by 2014. And that's very similar to what we see in the labs here in Australia. We're getting about 30,000 samples a year. And we're not by any means a high vitamin D lab. There are labs that do as many as thousands a day. So it's quite a lot. And that has fairly large implications for a clinical chemistry lab because vitamin D is not a particularly easy thing to measure. It's bound quite tightly by a binding globulin. There are metabolites that can mimic it, so immunoassays can struggle sometimes. So in the old days, when we used to only get 10 samples per week, we would do a fairly extensive solvent extraction to get the binding globulins off. We'd separate the metabolites out by chromatography and do fraction collection, and then we'd do a radioisotope immunoassay on the fraction to measure it. But when you start increasing the number of samples up to 100 samples a week, this becomes very difficult to do for a standard laboratory. You just don't have the staff or the ability to do it. So many labs just dropped out the chromatography step. It wasn't as good as the older method, but it was fit for purpose for what they needed. But then when you start getting to thousands of samples, we can't really afford to do any of these things because they just take too long and there's an awful lot of radioisotope going on. So in general, most labs around the world turn to automated chemiluminescent immunoassay platforms. So these are big boxes where you just pour samples in one end and loads of numbers come out the other side. And that was the only way that a lot of labs could do it, to keep up with the vast amount of samples that were coming through. So I suppose the question is, well, what's the problem with doing that? And to sort of illustrate that, I've got an example here of a patient where she was known to have fairly low vitamin D levels, and her clinician was actually a bone specialist, and she had numerous bone-related issues. So he made sure that she supplemented to keep a reasonably high vitamin D status. But then one of the samples that was taken, she had quite a low vitamin D level, And that concerned him, but she swore to him that she'd been taking a supplement, so he requested a second sample be taken. And this second sample had quite a larger amount of circulating metabolite, which made the clinician question the result that we'd sent out on the Monday. So we repeated that sample, and this time we got a very different result. And that called into question all of the samples that were run on the Monday. Now, worryingly, the quality control material that came with this immunoassay gave us very similar results on the Monday and the Thursday. So we're pretty sure the calibration hadn't drifted. So we measured the Thursday sample again, and this time we got a different result again for the Thursday sample. And then we kept repeating the measurement on that Thursday sample, and we kept getting different results. So obviously there's an issue here with a particular patient sample where the immunoassay just simply isn't able to give a very good result. And the clinician by this stage is obviously getting quite irate and asked us, well, what is the result in this patient? And the only answer we could really give them was, well, it's somewhere between 21 and 53, which, as you can probably imagine, wasn't quite the answer he was looking for. Now, this isn't really new, this information. Back in 2008, there was a survey done by the College of American Pathologists where they sent out a sample out to numerous laboratories. And for chemiluminescence immunoassays, they got a wide range of results back for the same sample, going from 102 to 240 nanomoles. So we knew that this assay could give quite variable results. And even recently, this is a distribution from the Vitamin D External Quality Assessment Scheme, DQAS. And in this scheme, there's about 1,000 precipitating laboratories. There's quite a number of different methods. Now, the CV at the bottom there of 16% seems a little bit large, but actually that's quite good for this assay. The CVs used to be considerably worse than that, up around 25 to 30%. But what's still worrying is the range of results that you could get from these different labs. Because for that same sample, some labs were reporting 39 nanomoles per liter and some were reporting 176. So there's still quite an issue here with measuring this metabolite properly. And that's where HPLC with tandem mass spectrometry really comes into it. And I've put a quote here by Graham Carter, who runs the DQAS scheme. And I particularly like the second paragraph where Graham says that LCMS is a welcome antidote to the onward march of ever simpler methods that have sacrificed analytical rigor on the altar of expediency. That's quite impressive. I think Graham may have missed his calling in life if he's going to write things like that for clinical journals. But I think we know where he's coming from. So many labs decided to make the move to LCMS, tandem mass spectrometry, using triple quadrupole instruments for measuring vitamin D. But there's always the issue with just the sheer number of samples. It's often quite difficult to do, so you need as simple a method as possible, which takes the least amount of staff time and instrument time to get all the samples done. So this is just a picture of one of the LCMS systems we have in our lab. The blue box there is the triple quad mass spectrometer, and then on your left there, that is a very large HPLC unit because we have a large order sampler because we do quite a lot of samples, and we have 2 stacks of pumps because we generally do a lot of online solid phase extraction in our labs. So in order for us to do all of the vitamin D samples that we get in the sort of time frame that's acceptable, we have a very simple sample preparation, which is essentially just a protein precipitation in a filtration plate, where we take the plate, we shake it after we add all the components together, and then we centrifuge it into a collection plate, and then put that collection plate onto the LCMS. Now, manually, that can take about 40 minutes to do about 84 patient samples, which isn't too bad. And we've actually moved that onto robotic platforms now, so that's considerably faster. Unfortunately, just doing a straight protein precipitation leaves you with a fairly dirty sample. and that dirty sample contains an awful lot of phospholipids. So we have to clean the sample up online on the instrument, and we do that by using online solid phase extraction. So we have one set of pumps on the HPLC which pump your sample through the autosampler to a switching valve where it goes onto an online solid phase extraction cartridge. Your vitamin D analytes are retained and everything else is sent to waste except for things like phospholipids, which are quite hardly retained. And then the second set of pumps kick in, the valve switches, and we push the analytes off the SPE cartridge onto an analytical column and then into the mass spectrometer where they're measured. And then before the phospholipids can come off, we switch the valve back again and send them off to waste. And so that's worked pretty well for us. We've been using that for a number of years, that process. But there are some common issues that affect pretty much all labs who do LCMS for vitamin D. And that is whether or not the analysis they do is suitable for infant samples, which I'll go into in a moment, and also how have they harmonized their method, because there's 100 different methods out there for doing vitamin D measurement by LCMS. So how are we ensuring that we've got traceability of our calibration and that we're all getting the same sort of results? Because there's no point us all getting different results like the immunoassays did, because that doesn't help anybody. So infant samples, why are they a problem? Well, a lot of infants actually contain an epimer, the 3 position, of 25-hydroxy vitamin D3. And so I've got the 2 structures here, and if the only difference between these 2 structures is just the orientation of the hydroxyl group at the bottom. And the consequence of that is that these 2 analytes, we don't see these in adults, the epimer. We've done a lot. I know a lot of papers out there say they have seen some, but we measured a number of thousands of adults, and we didn't see any of note in this analysis. I put a reference down the bottom there for that study. So we don't actually see that. So generally we run all of our adult samples using a method that doesn't resolve the epimers. But we do see the epimer in infants. Now this epimer, we don't really know what it does. There's some evidence that says that it's actually inactive. There's some evidence that says that it can suppress 25-hydroxy vitamin D action. But it's general consensus that if you're going to measure 25-hydroxy vitamin D3 in infants, then you need to be able to separate it from the 3 epimer. So in order to do that, we used a separate type of chromatography. So the chromatography on the top is standard reverse phase using a C8 column. The lower panel, we've used a PFP column, the Ascentis Express F5, and this was an application that Craig and his team at Sabelco put out, and we simply modified it so it would work with our online solid phase extraction process. So you can see the 1 minute, there's a dotted line there that indicates when the valve switches for online solid phase extraction. So the lower method's great because it separates the epimers, but you can see there it's 8 minutes long. And that's a bit too long for us to actually process all of our samples. So we generally had a 2-stage process where we would measure all of our adults with the top method, and then we would run a second method for all of the infants. And that's not particularly ideal, especially when you might get a transcription error and an infant sample might go through the wrong method. So one suggestion that we had from Craig was thinking about using hybrid SPE. I won't go into this in any great detail, but this is not SPE in the sense that we sort of load samples onto the column and then wash it and then elute them off. This is more like a extensive filtration step. And in this case, you would precipitate the protein in your sample and pass the precipitate straight through the hybrid SPE, where it would filter out not only the precipitated proteins, but it would actually trap the phospholipids as well. Now the idea here was that if we could use a hybrid SPE to replace what we were doing with our online solid phase extraction, then we could shorten our epimer resolving method so that it would be able to replace this 2-stage process that we were using for our routine analysis. And the other benefit, obviously, is you've got a little bit more to play with your chromatography when you don't use online solid phase extraction. So you can actually speed things up a little bit. Now, we appreciate that you can actually do the protein precipitation inside the hybrid SBE plate, but we're a clinical diagnostics lab, not a research one, so we wanted to check whether or not this would work as quickly as possible. So rather than do the precipitation stage inside the hybrid SBE, we actually just stuck the hybrid SBE plate in between our precipitation plate and the collection plate, kind of like sandwiching it in there, and then put it in the centrifuge and spun it as we would our normal samples. So basically it added absolutely no time to our sample preparation whatsoever. And the results came out looking pretty good. On the top panel here we've got our routine method for adults, which doesn't resolve the two epimers. The next panels down we've got the epimer resolving method that we use on infants, which is obviously 8 minutes long, but can separate out the epimers for both vitamin D3 and vitamin D2. And then on the bottom panel, you'll see that we don't have a dotted line here because we've omitted the online solid phase extraction step entirely. And we've just used the hybrid SBE. And we've got quite good separation between the epimers at a reasonable time frame. Like our original method was 2.4 minutes for the analyte to elute. And you can see at the bottom there, the analytes are eluting at about 3.1 minutes. So we could actually use this hybrid SBE method to replace both of our two-stage process from before. And if you want any more details on that, I've put the reference there at the bottom of the slide. Now this is all well and good that we're able to separate the epimers, but we need to make sure that we've actually got methods that match up. So on the top here we've got a number of adults or patients between the ages of 1 and 91 years where we analyze them by our normal frontline method and by the proposed hybrid SBE method. And then below we've got the comparison between our epimer resolving method for infants and the hybrid SBE method on a bunch of infants that did actually have epimer in them. And you can see we get really good agreement on both of those. So one other thing we wanted to do when we set this method up was make sure that the results that we get, okay, I mean, we've got good agreement here, but we need to make sure that we're actually getting results that match what we should see from the standard reference material from NIST. So this is a frozen human serum, which contains the vitamin D metabolites and the epimer, where they've been measured by higher order reference methods, and you can test your methods against these materials to ascertain your bias. And we've put that data, we actually got quite good agreement, and we put that data in the paper as well. The one thing we haven't got to yet, and this is sort of on the future work list, is the CDC have, because so many of the vitamin D studies out there, there's been some questions raised about like how good the data is based on the method they use to measure it. And to get around that, CDC have released this standardization program where you get sent out a number of samples that you measure with your method of analysis, and so long as you get results that are between about 5% of what the higher order reference methods get, then you're awarded with a certificate from the CDC to say that you can measure vitamin D properly. So that's, I mean, this is something that we would do if we started a large research study, but it is something we're quite keen to get involved with. So, okay, there's a couple of things I'd like to say just to be careful of, and that's, it's become very common, well I've certainly noticed it, for manufacturers of vitamin D, 25-hydroxy vitamin D assays or calibrators to state that they are traceable to the NIST reference era. But they don't provide the data, so the statement's almost meaningless in my eyes. Or they'll say things like they're enrolled in the CDC's vitamin D standardization program. But to be honest, my mother got enrolled in that standardization program. It doesn't mean she'll get a certificate. So unless you see the certificate or the bias data, then those statements, you shouldn't put too much faith into them. So if you're thinking of doing a study that involves 25-hydroxy vitamin D measurement, I would sort of suggest that you look for a lab that can do it by LC mass spec. And once you find one, if you're going to measure vitamin D in infants, make sure they can separate the 3 epimers. And if they don't know what you're talking about, then find someone else to measure your samples. And if you're going to be doing a big population study, make sure the lab who's doing your measurements has been approved by the vitamin D standardization program, and actually ask to see the certificate. Because trust me, if they've done all the hard work to get the certificate, they'll be dying to show it to you anyway. But if you're taking it just to a routine diagnostics lab to do a small study, then at least just find out if they've determined their trueness of their method against the reference sera. And actually ask to see the data. There's no reason why they shouldn't show you. So with that, I'd like to quickly wrap up and just thank the guys at Sigma and Sapelco who helped me set up this method for us to run, my colleagues at the Prince of Wales Hospital in Australia, and from Cambridge University Hospital over in the UK. And with that, I'm going to pass over to Craig, who's going to present the rest of this presentation.
Okay, thanks, Mike. I appreciate that. That was an excellent talk on the actual implementation of the vitamin D assay. What I would like to do now is to take you through the process of actually how we do the methods development for the vitamin D metabolites. This is something that is a routine for us here in our facility at Sapelco, is that our applications group works specifically with customers to develop solutions for their assays. And so I wanted to give you a little bit of an insight on how we go about doing that, and particularly here for vitamin D metabolites. So one of the real questions, or one of the issues that Mike had brought up, was the resolution of the epimers, particularly for infant samples. Okay, so back to the process. So we're going to screen through the different stationary phases to look for the resolution of the vitamin D metabolites. Now, if we look at the compounds here, this is a breakdown of the different metabolites we're looking at. The D2, the D3 hydroxy, 25-hydroxy metabolites, along with their associated epimers, and along with the dihydroxy metabolites. Now, as you can see, if you look at these structurally, they're very similar, fairly difficult to get enough selectivity out of a traditional reverse phase separation. The cases for the dihydroxy metabolites, of course, they're going to be a little bit easier to be able to separate. But the epimers and the 25-hydroxy metabolites are going to be more difficult, just structurally speaking. So the process that we used to do the methods development was to screen different stationary phases. And what we're looking at are the resolution of critical pairs of the vitamin D metabolites. The first pass is to do initial gradient screening. This is a very common practice for reverse phase chromatography. And then from that, what we've tried to do is then develop an isocratic method that might be a little more robust for the final assay. The experiments, what we did was we looked at the pentafluoro phase, we looked at a phenylhexyl phase, along with a cyano phase, and then looked at different stationary phase organic modifiers to see what the impact was on selectivity with those different stationary phases. There have been publications using cyanostationary phases for the separation of the vitamin D metabolites, but those assays typically tend to be quite long. You're talking anywhere from 30 to 40 minutes to be able to get resolution of the epimers during using the cyano phase. So we wanted to see if we could do a little bit better than a 30 to 40 minute assay for the epimer resolution. Just to give an example of what the screening protocols looked like, we did gradient elutions using methanol, ethanol, and acetonitrile. Each one of those conditions was modified slightly based on the elution strength of the organic solvent, and so we could get a better indication of that if we were getting resolution of the vitamin D metabolites. Temperature and flow rates were kept constant throughout the assays. And the initial screening was conducted using a UV detector, with the ultimate goal is we're moving this into a mass spec assay We felt it was just a little bit easier since these compounds have great chromophores on them. Won't have a problem seeing them by UV. We weren't going to tie up our mass spec instrument just doing initial screening for this. But with that, knowing that the metabolites are isobaric, and that is the problem why we have to separate those for the LC-MS analysis, what we decided to do is we set up the initial screening assays. We separated the individual isobars from each other. So as you can see here for the first vitamin D mix, we have the epimers together. Their masses are different, 412 versus 400. And if you look at mix 2, then we have the two alpha hydroxys, the D2 and D3, and of course their masses are quite different. That just kept it a little bit easier for us to do tracking in the UV spectra of the chromatograms, so we can get positive identification of the corresponding peaks. So just to give you an example what the screening looks like here, this is one of the conditions on a phenylhexyl stationary phases using an ethanol organic solvent. You can see on mix 1 we have our 2 epimers. Mix 2 is the dihydroxys, and mix 3 is the 25-hydroxy D3 and the alpha hydroxy vitamin D3. And the windows that are drawn around these peaks represent the isobaric compounds. So the pair in red represent the isobaric pairs of the 25-hydroxy D3 and the epimer. So you can see here on the phenylhexyl stationary phase, we have direct overlap of those compounds. So this method is not capable of resolving the epimer from the 25-hydroxy D3. In the same case, we are also monitoring the 25-hydroxy D2 from the epi 25-hydroxy D2. And again, the case was we could not resolve these epimers from the 25-hydroxy D2 under the stationary phase. So when I described is that we're looking for critical pairs, these are the critical pairs that we're monitoring to ensure that we have proper resolution of these metabolites so we can get proper identification. So we set up a matrix. Well, I guess the next slide here is what actually shows a method that we used on the Ascentis Express F5. Now this is with a methanol mobile phase, and you can see here the only coelution that we have is between the 3 epi 25-hydroxy D3 and the 25-hydroxy D2. Now this does not cause a problem for us because these compounds are easily resolved with the mass spectrometer, so we can get proper identification. So our epimers are efficiently resolved away from the 25-hydroxy metabolites using these particular elution and chromatographic conditions. So what we had set up was a matrix plot essentially looking at the minimum isobaric resolution based on stationary phase and based on the mobile phase combinations that we used. So what we were looking for is a minimum resolution of 2 between the epimers and the 25-hydroxy metabolites. And so this table just goes through to show the different stationary phases along with the corresponding mobile phases and the resolution that we achieved. As we can see, the phenylhexyl, regardless of the mobile phase combinations, was not able to have resolution of the vitamin D metabolites. We did see some resolution on the cyanophase, but it still wasn't sufficient to be able to get proper identification and have confidence in the data that we were actually identifying the epimer away from the 25-hydroxy metabolite. The only combination that we came up with that was really sufficient was using the fluorinated phase with a methanolic mobile phase modifier. Even with acetonitrile, we were able to get some resolution, but it still wasn't sufficient. It was only with the methanolic conditions that we found to have sufficient resolution to be able to do positive identification of the vitamin D metabolites. So this is just a breakdown of the summary I just went over. What we did was from the screenings, we had got some initial conditions that we felt that we'd be able to get a resolution of the epimer from the 25-hydroxy vitamin D metabolite. We wanted to further transfer those conditions to see if we could better optimize them to develop an isocratic method, and also look at other impacts that would improve sensitivity, particularly for the mass spectrometer. So now what we're looking at is we're interested in getting the best ionization out of the vitamin D metabolites out of our mass spec. And so if we go to the next slide, what we're showing here, this is a chromatographic separation of all the vitamin D metabolites. These are all summed together into one chromatogram. And what we're looking at is a comparison of the ionization response of all the metabolites using different modifiers. And the comparison is using ammonium formate versus an acidic formic acid mobile phase. Now, all these assays were conducted under ESI, positive ionization mode, and this was on a time-of-flight mass spectrometer. So we wanted to see what impact that the buffer or the acid would have on response. And what we can see here is that regardless of the modifier, there really isn't a change in selectivity on the vitamin D metabolites using the different modifiers. And that's kind of to be expected. There's no ionizable sites on the vitamin D or this metabolite, so we wouldn't anticipate really too much of a selectivity change just based on pH. So we were pretty confident we could keep our resolution. What was surprising was the response difference between the modifiers. And if we see here that the ammonium formate modifier had almost double the response of that of the formic acid. Now, formic acid modifiers are typically used in LCMS. I mean, it typically helps to improve the ionization, particularly for basic compounds. But in this case, with the vitamin D metabolites, what we found was that just a little bit of the ammonium formate present dramatically improved the response of all of the metabolites. So to further show, this is honing in towards the final method conditions that we had developed. What we're showing here is the separation of all 6 vitamin D metabolites on the Ascentis Express F5. And what I've done now is broken the chromatogram down into the compounds based on their mass to charge ratio. So the top chromatogram shows the 25-hydroxy D3 along with the epimer and then the 1-alpha hydroxy D3. So plenty of resolution. We have good positive identification of all 3 of these isobaric compounds, and that's going to result into a pretty robust method that we feel very confident in the data that we generated. Going through also, we look at for the 25-hydroxy D2 and the epi D2. Again, it's not as common to look for the D2, but it was reassuring to know that these conditions were sufficient to be able to do that resolution should there come a need to be able to start monitoring the epi D2. And then, of course, the 1-alpha, 25-hydroxy D3, and 25-hydroxy D2, no issues in resolving those conditions either. So we felt pretty confident that now that we've developed optimized chromatographic separations, we optimized the mass spec conditions to be able to get the best response out of ESI ionization. So the next part was to move forward and look at the sample processing portion of that. Now, as Mike said, typically what we do for vitamin D assays is just do a protein precipitation. It's a quick and easy method to do that, specifically when you're looking at high volume samples. But we know that it's not the most robust or most effective method for sample cleanup, particularly for LCMS. And it might touch base on a little bit the impact that protein precipitation can have on ionization, particularly for phospholipids. So that's a real issue out of plasma serum samples, that phospholipids co-eluting or eluting with your target analytes. So we wanted to explore how we can improve the sample preparation and improve the robustness of the assay by utilizing a method to be able to deplete the phospholipids. So the experiment that we conducted was to take human serum samples that they were spiked at a fairly high level, and then these were passed through the hybrid SPE plus plate. So the process was to add the plasma, add a crash solvent, to mix the sample, and then what we did was you draw the supernatant off of that and pass that directly into the hybrid plate. Now the plate can be used with other configurations. You can do crashing directly into the plate, but we felt we wanted to try to replicate best as what Mike was doing and do the crashing of the proteins offline. And so just to give you a breakthrough down of what the hybrid SPE plate looks like and how it works, it is a 96 well plate format. It is designed with a Teflon frit on both the top and bottom of the well plate. And then there is a packed media that is in between that is the scavenger to remove the phospholipids. Now, the design of this plate is quite unique because it acts as a depth filter and allows for direct removal of precipitated proteins from plasma samples. The Teflon configuration of the frits allows for plasma samples to be added directly into the well plate, and so you can do direct in-well protein precipitation, or you can do it offline also. But as the design has been set up, is that sample will not pass through into the packed bed until vacuum is applied. The hydrophobic nature of the Teflon prevents sample from passing through, so we can ensure that we have good recovery and consistent flow through the well plate. But the real heart of the technology really is behind the stationary phase that's there. It's a zirconia modified silica. And the way this technology works is the use of zirconia and titanium used for isolation of phosphopeptides has been long been known, but it has limitations in that there's very limited capacity with titania, pure zirconia, to have enough capacity to extract a large amount of sample. So what we did is we took from the knowledge of the utility of zirconia and then took our expertise with surface modifications, and then we grafted zirconia onto the surface of the silica particle. And what that allows us to do is it gives us much higher surface area, much higher capacity. So now we can start looking at targeting depletion of phospholipids because they're in such high abundance in plasma samples, depleting them from the sample completely, and then having a fairly clean sample for our LC-MS analysis. Now, what's unique about the zirconia surface also is that it's very selective. It's a Lewis acid-base interaction between the phosphate moiety of the phospholipids and the zirconia surface. So we have very selective removal of phospholipids, and that allows us to have excellent recovery of our target analytes. So it's not a traditional Lewis Bronsted acid-base interaction that you would see for some cation exchange resins. This is specific to Lewis acid based on the degree of unsaturation for the electron pairs. So highly selective towards phospholipids. It has high capacity, so we can get a very clean sample from our plasma samples. So on this slide, what we'd like to show is just the comparison of the same plasma sample. One has been processed just doing protein precipitation. The other has been processed using a hybrid SPE plus plate, and just showing the comparison for phospholipids detected in the samples. What we're doing here on this particular instrument is we're looking at 6 specific phospholipids that are representative of both the lyso and glycerol phospholipids, so singly chained and doubly chained phospholipids. And you can see here on the hybrid SPE, there are no detected phospholipids present in the plasma samples. As compared to protein precipitation, there's a significant amount of presence. And most interestingly is that the phospholipids elute directly in the elution range for some of our targeted vitamin D metabolites. So this would be of concern, particularly for the method development. When we look at potential matrix interference, this would cause some concern since we have direct overlap of our target analytes with our known matrix. So on this slide, what I'd like to show is just a comparison of the analyte response or recovery of the metabolites versus protein precipitation. In the first column, what we show is just the hybrid SPE plate that we've passed just a standard solution of the vitamin D metabolites through. And this is just to show that we have excellent recovery of the metabolites. They're not sticking onto the plate themselves. As Mike said, the plate is not like a traditional SPE plate. You load your sample, you load the crash solvent, mix the sample and apply vacuum, and that's all there is to it. There's no washing, there's no secondary elution of the plate. Basically, it's just apply vacuum, pull the sample through, and then the sample is ready then for analysis. So it's a very simple process, and again, we wanted to show that just with standard solutions that we don't get any retention of the vitamin D metabolites onto the stationary phase. If we move this now to the middle column, if we look at the recovery of the vitamin D metabolites through the hybrid plate, this is out of plasma samples spiked at 25 nanograms. As you can see, we have excellent recovery for all the vitamin D metabolites through the hybrid plate. In comparison with the protein precipitation method, you can see there are cases for the 25-hydroxy-D3 and the epimer. We see significant reduction in response of those metabolites using just protein precipitation. And again, this is due to direct overlap of the phospholipids. As I said in the previous slide, the phospholipids elute directly in the range of the vitamin D metabolites. So using the hybrid plate sufficiently removes the phospholipids, and now you have a much better response as compared to the protein precipitated plasma sample. So with that, I'd just like to go just in a bit of a summary then with the hybrid SPE plate. It does demonstrate, it shows the ability to deplete phospholipids, resulting in no matrix interference and better limits of detection and quantitation using the sample prep method. It also adds to time savings too, because as Mike showed, we can simplify the sample prep a bit and actually speed up the assay by not having to do tandem or two-dimensional LC for the sample preparation. For samples that had been processed using just protein precipitation, in some cases we saw as much as 40% reduction in the analyte response. Even though the concentration is the same and it's the same plasma sample, the phospholipids were reducing the response to those metabolites, resulting in higher error and less robustness in the assay. I think the real message to take home is that, with the advent of mass spectrometers, that we've gotten the specificity and the instrumentation, but there still is need for chromatographic resolution of analytes. And I think the vitamin D metabolite application is an excellent example of that, where it's still necessary to chromatographically resolve isobaric compounds that would otherwise not be able to be resolved on the mass spectrometer. So I think this is a good combination of showing how selectivity, both in the sample preparation along with chromatography, adds to the benefit of the assay for LC-MS. And with that, I thank you for your attention. I thank Mike with the assistance for this presentation. And what I'd like to do is move to the next slide and turn it over for questions.
All right. Thank you, Craig, and thank you, Mike. I think the back-to-back presentations worked really well, and you both presented some very complementary information, and I hope it's been very useful to the attendees. So now is your time. If you need to ask any questions, please do so. You can enter it in the question box and just submit it, and we will discuss it. We have a few minutes for Q&A, so we'll be happy to bring up your questions, any issues you may be running into if you're working on vitamin D analysis, or anything more general is fine too. We'll be happy to discuss that. And also a quick reminder that the webinar will be archived online, but you will not be able to download any slides from the archive. So if you have if you have questions about the slides, if you need a copy of the slides, you have our speakers' email addresses on your screen. So please make a note of that, and I'm sure they'll be able to offer you additional guidance if you have any questions coming up even much later after the webinar. So let's begin with a few questions, and maybe I should pose this question to both of you. So we talked extensively about the FPE plates. So do you see a plate-based standard sample prep as being a new trend going forward? And if you do, what other applications come to mind? Craig, do you want to take a stab at it?
Yeah, Craig, do you want to start, and then I'll give a clinical perspective. How about that?
Yeah, sure. Yeah, we've seen the development on the hybrid plate several years ago, and it was really addressing a need within the market because of the phospholipid issue for mass spectrometers. But I think underlying, even for any type of clinical assay, when you're dealing with some type of population, you're going to have to do sample preparation of some sort. Just the variabilities that are persistent in patients, you need to have a way to be able to controlling or mitigating the amount of interference that could be introduced into the assay. And I think one piece that is often overlooked is that sometimes you can have a dirty sample, and if you continue to introduce that into your mass spectrometer, you'll have decreased response, but you can almost plot that with control samples. It's to be anticipated. But when you're dealing with a diverse population where each patient's profile can be a bit different, now this inherent variability just in the patient population translates to more variability into your assay. So sample prep becomes even more important at that point because you don't know what the variability from one population to another, you don't know how different their profiles are going to look. So cleaning the samples up properly in the beginning, I think, is really important to having a robust method. So, Mike?
Yeah, I think I totally agree with that, and I think from my own perspective, having done ion suppression studies on large numbers of patient populations, the thing that's most striking is the amount of ion suppression variation from patient to patient. And it can be quite staggering. You can get some patients with an enormous amount of ion suppression, be that from phospholipids or from other sources. And I think if you don't do enough sample preparation to reduce that, then how are you ever going to know what your lower limit of quantitation is? Because your lower limit of quantitation should be the amount that you think you can measure when the situation is at its worst. So if you're going to make a robust method where you're confident of the results that you're generating, then you need to do as much as you can to minimize these effects. As far as like this plate-based technology being a way forward, it's kind of weird because initially we did a lot of the time we actually moved to SPE plates as a way of getting away from extensive and difficult liquid-liquid extractions to simplify things. And the other benefit with using like standard SPE was it gave us the ability to concentrate up our samples. But as the years have gone on, our mass spectrometers have got far and far more powerful, and the need to concentrate our samples for a large number of applications has actually become less. I mean, it's still there for some of the more difficult things, but we can actually get away with more dilute samples. And so that then sort of enables us to look at other options. I mean, to get things to go faster and quicker, we looked at online SPE, but not everything's applicable for online SPE, and it does make your run times longer. So the ability to have a plate that cleans up your sample without adding any extra steps and produces basically what is effectively a precipitated protein sample that is much cleaner actually provides quite a larger benefit for us because it didn't increase throughput in the slightest but made everything a lot faster. I think the only thing I would say is that you just need to be careful that you've got nothing on the analyte that you're looking at that might actually stick to the hybrid SPE plate itself. But when you're looking at the neutral guys, like things like vitamin D and testosterone and compounds like that, they are very unlikely to stick to the hybrid SPE plate. So they're pretty good candidates for this kind of technology.
Right.
No, yeah, that's a really good point. And how do you know if something has indeed remained behind on the plate? And Craig, Okay, go ahead.
Yeah, usually we do a recovery assay. So we spike in the sample to a known amount and we check it through, and if nothing comes out the bottom, then we know it's stuck to the plate.
I see.
Yeah.
Okay.
We do the same thing too. I mean, that's part of the presentation, just showing standard solutions. That's always the starting point for any assay. We work with pure standard solutions going through the plate just to establish if there is recovery issues. And what we found with that material is that there are maybe 3 or 4 different protocols that we suggest to use if they have low recovery of some compounds that we suggest trying. And really the problem compounds typically be chelators. So anything has a chelation site or a carboxylic acid that may bind up onto the zirconia surface. And we have protocols to modify that. Just the addition of formic acid, or even sometimes we put a little citric acid, and that's sufficient to improve the recoveries of some analytes that would be bound up onto the stationary phase.
I see. So how many times can these plates be used or reused? I would say?
So once they're a one-time use plate, and certainly for a clinical setting, you would only ever want to use a plate once, just because of concern for the plate and make sure your data integrity.
Okay. Yeah.
Yeah, that would cause quite a lot of problems if we started passing different patient samples through the same wells.
All right. What about some of the other factors that people should consider? If you're looking for very trace amounts of materials, what if you have limited sample volumes? Can you talk a little bit about those types of issues? Any advice?
Yeah, I'll chime in here quick, Mike, and then I'll let you follow up. There's with this technology, there's an interest in the industry now to try to do miniaturization for sample prep. So the samples are becoming much more precious. We need to do more with less. We want to be less invasive with our patients. And so there's been a focus to try to miniaturization of sample prep devices. And so we've seen that. We've addressed some of that with the hybrid plate. There's actually different configurations of these plates. So we have a plate that's designed for very small volume samples. So 20 microliters or less of plasma samples can be used with the plate. And the technology is still the same. It's just based on the configuration to be able to get a better recovery. One thing that is unique, and I said because this is not traditional SPE, there's no conditioning of these plates. So there is a little bit of volume holdup within the well plate, and so you will lose a little bit. So that is a big concern with small volume samples, and again, that's part of the reason why we've developed a small volume plate. But miniaturization is certainly a focus in the industry. We want to do much more with less, and we have to be there to meet the needs of our customers' expectations.
Sure. Mike, did you have anything to add?
No, I think that's pretty standard. I think, like a lot of us, you only have to talk to people who work at children's hospitals to know that they deal with very, very small samples. So miniaturization is often the big keyword. But with these plates, some of our experiences with it was that we could always do what we did with a lot of other things, where we pass it through with a reasonable amount of solvent, but then we just dried that eluate down before we went to inject. So we didn't get such a sample dilution effect, and that seemed to work pretty well as well.
Okay. Well, we have kind of reached the end of our webinar time, but I would like to ask one quick question, because everybody has a different sample that they're working with and different applications. So how much customization is possible when it comes to sample prep? Craig, in your experience, since you're involved with a lot of method development, do you think there's a lot that you can do to make it possible for a certain lab to do things the way they want to do it?
Yeah, I think that's one area with sample preparation. There is a large area for customization. Based on surface chemistries, a lot can be done with ion exchange resins, filtration media configurations. So I think that's probably one of the largest growing areas for any type of LC-MS consumables is the sample preparation portion of that. So I can see that continuing to grow on. So.
Okay, that's really good to know. And Mike, did you have to do any sort of customization, or was it just?
On this application, luckily for me, no, because Craig had done most of it for me. And luckily, we actually were able, in this instance and in one other, we were able to just basically take our standard protein precipitation protocols, which we'd already done, and just basically add the hybrid SBE plate to that experiment, and that worked really well for us. So we didn't really have to do a lot of customization with this. But, I mean, that protocol that we used seemed to work for a couple of other analytes as well, some androgens. So, I think it didn't need a lot from our end.
Okay. All right. Well, as you can see, Craig and Mike have had a lot of experience, working out all the kinks. So definitely feel free to reach out to them, and if there is anything that's specifically applicable to you, your application, your sample, I'm sure they'll be happy to help you out. So thank you once again, Mike, Craig, for putting together, I think, very informative talks. It came together really well, and for taking the time to address all the questions. To those of you online, thank you again for your time and attention. And just a quick reminder that the webinar will be available for access at least for a few months. And if you need the slides, you will definitely have to reach out to our speakers directly. And please keep checking the Lab Manager's website, because we do have a lot of webinars that are already archived there, which you may find useful, and we are continually updating the site with more information about new webinar topics. So until next time, everyone, goodbye and good luck.